and the intersection of these. Nick and Dave are from the University of Birmingham, as they will explain to you. There's a lot going on there from the point of view of putting together robots and AI in general. And Nick has started to make a big name for himself in this field, so we're really interested in hearing what he has to say on this. So, yeah, leave the floor to you. Thank you very much.
Cool. Thank you very much. Yeah, thank you for the invitation to come and talk to you. It's exciting to be stood in front of, I guess, the up-and-coming great brains of planning. And part of this talk or tutorial will be to try and get you excited about working with robots. And part of it will be about trying to show you perhaps the breadth of techniques and sort of skills necessary to successfully apply planning to robotics. So there's a long history of planning and robots being associated, going back to Shaky. But actually, it's reasonably rare to see task planning successfully applied to real robot systems. There are some kind of counterexamples to that, and I think one of the reasons is that it's actually very, very hard to bridge the gap between the techniques that are popular in the planning community and what really works well on robots. That's not something we're necessarily going to address in detail, but what you'll see today is rather than a broad, well, rather than a tutorial where we go through every possible technique you could use, we're going to give you an example of, just some point in a space of possible techniques that work well on robots. So we're going to talk in particular about the techniques we use within the Strands project, which is a European project which I'll talk about very briefly in a minute. And we're just going to sort of talk you through the different parts of the system, the reason that these bits exist, and give you a bit of a grounding in some of the underlying principles that work in it. So the structure of the tutorial will be 45 minutes of me, a better 45 minutes from my colleague Dave, who'll talk about a different bit of the system, and then an even better 90 minutes of practical work, where we've prepared, hopefully you've seen, but we'll come back to that in a minute, we've prepared a sort of tutorial where you can actually work with the system we've built in simulation. So the idea is really to give you a grounding in the first half of the underlying techniques that are in the system. So give you enough understanding that when you start working with the system, you understand what you're doing. And in the second half, you get some practical experience. I'll say that the practical stuff won't be easy, both through logistical reasons and through the technical reasons. And the first half you might think is, why aren't they covering this and why are they covering this? And again, this is because we're showing you kind of an instance in a space of broader possible techniques. What I would say though is please ask questions. Have you been a talkative bunch so far? That's a no. Okay. So if no one talks to me when I give lectures, I slowly wither and die. So if I don't get any responses or if I don't get any questions, it's just going to be really tedious for all of us, particularly on a hot afternoon like this. So please, if there's anything you want to know, if I'm unclear, if English isn't your first language and I'm going super fast, which sometimes I do, please just stick your hand up, stop me, slow me down. Or even if English is your first language, sorry, I should also allow English speakers to not understand me. So please, I'd rather this was interactive. I'd rather we took as much time as necessary to cover the stuff you need to understand. So please, take advantage of me stood here and really ask me questions. Is that clear? Yes. Okay, more noise. So, what we're going to talk about today is work that we're doing in the Strands project. So the Strands project is a European project focused on long-term autonomy on mobile robots. So here are some examples of our robots here. This is Bob in an office in Tewkesbury in the UK, and this is Werner in the Haus der Barmherzigkeit care home in Vienna, in Austria. And we've been working at putting these robots into these environments such that they can exist for weeks and months at a time. So we're not interested in just building a cool system to demo for 10 minutes to a funder, or a system that we can use to make a video for ICAPS or ICRA. What we want to do is actually build real systems that run for long periods of time in challenging environments. So when people say challenging environments, they typically mean, nuclear reactors or the moon or something. Actually, offices and hospitals are equally challenging for other reasons. I say that because I got a phone call this morning that one of our robots, Betty, who's in an office in Milton Keynes, crashed into something in the night and ran out of batteries. And so she died, unfortunately. So we're very sad for Betty, but we're resurrecting her today. But there's lots of challenges in these environments as well, from a planning perspective and from a robotics and kind of practical perspective. Okay, so yeah, the work we're going to talk about is actually the work when you see these things driving around. That it's the planning framework, it's the executive framework that's actually choosing what these robots should do next, choosing how they move through the environment. So what you're seeing here are robots driven by the techniques we're going to talk about today. Okay. So our overall system looks a bit like this, and we're going to zoom into parts of it in a minute. But I'm just using this really as an opportunity to plug what we're doing. In that everything you'll see today is open source and released in binary form for Ubuntu 14.04. So if you get at the end of this, you get really excited, even if you haven't done the practical bits, you're like, actually, I really want to work on robot systems. I want to use these kind of bits. If you just Google for the Strands project, you can download all our stuff and have everything up and running on your own robot, your own simulation very, very quickly. So, I mean, it's one of the big things I think the planning community does very well, and it's something the robotics community is learning to do better as well, which is sharing stuff in a form that you can reuse. So you can only really learn from the development of each other through papers, but also through the application of their software systems. So there's lots of stuff in the project I'm not going to talk about. There's things to do with databases and qualitative spatial representations and predictive modeling and semantic mapping and all sorts of stuff. We're not going to talk about that. What we are going to do is we're going to zoom in, because this is ICAPS and a planning conference. We're going to look at the kind of executive control part, the task level control part of the system. So for me, and this is something that I've followed through, I think, throughout my career, is when I see a robot doing something or a system doing something, I want it to be driven by planning. I want that system to have goal-oriented behavior and to be all its actions to be driven through planning. This is something actually is very hard in the robotics community to get across. So robotics people traditionally, I think, maybe Federico will agree, are quite suspicious of high-level control, task-level control. They like building low-level controllers that are fast and move the robot in predictable ways. They don't like giving up their whole precious robot system to something that sits on top and decides what it's going to do next. But ultimately, if we want our robots to provide effective services in human environments, those, the effectiveness comes from knowing what to do next, doing things in the right order, choosing tasks in particular orders, not over the next 10 seconds or 10 minutes, but over potentially days and weeks and months. So that's the angle that I'm really interested in from the planning perspective. It's not something we're going to go too much into today, but that's where I'd like to get to eventually. Not just thinking about a planning horizon, so typical robot planning horizons are kind of trajectories of robots or arms. Moving it up to the next task stretches your planning horizon up to minutes. What we're facing now with managing the battery level on mobile robots is thinking about kind of a 12-hour planning horizon. How can I choose what I'm going to do in the next 12 hours, given that I only know some of my goals, for example? So that's an interesting challenge. So when our robot runs every day, it'll have some things it has to do every day. It'll have some things that are given to it asynchronously during operation. And you ideally want it to know, and there's a third set of things which may be exploration tasks, things it can do if it wants to gather more information. And there's some big open problems about the best ways to balance those different types of goal-driven behavior, given you have limited resources, and you want to do it again and again. So there's some exciting problems in this big space. So this is kind of how we're encapsulating parts of those problems today. The four boxes change a little bit depending on which bit of the system you're looking at, but this is the sort of the version we've used most of. So we start up here with a routine. This is something that we found didn't really exist in the literature, and it's not something we've maybe thought about too much from a principled scientific perspective, but it's essential for what our robots require, which is every day the robot has a to-do list, effectively. So Betty in the office of Milton Keynes has to check between 6 and 9 in the morning and 6 and 9 in the evening whether there's anyone still at their desk. So they have a policy about lone workers, and they want the robot to check whether people are still at their desk. So every day between 6 and 9, that's what the robot's got to do. Then at the end of, by lunchtime and at the end of the afternoon, the robot should go around and check any shared working areas and check that those shared working areas, no one's left their bottle there or left the mug there. And then throughout the day, we also want to perform some updates with our mapping algorithms to certain bits of the world. We want to try and learn some objects from different bits of the world. And also we want to reduce the robot's uncertainty over estimates of its travel times through the world, for example. So there's some exploration times. Those things happen every day. So we have a routine structure which we can sort of procedurally specify the kinds of tasks the robot should be doing. So we say, look, here's a time window between 6 to 9 in the morning, and here are the 10 locations the robot should look at, and here are the operations the robot should perform at those locations. So we start with that kind of structure. You can think of that as a way of generating goals for the robot, okay? That's generating goals, but it's generating goals based on time of day, and it does that same thing every day. It's here actually that we would specify things like, okay, the robot doesn't work Saturdays or Sundays, so we flag that up in the routine and say, well, don't generate goals to the robot on a Saturday or Sunday. And for me, this is one of these areas of planning where people don't, it didn't always sit in the planning community, it was more broader AI, which is where the goals come from in a system. So typically when you see a piece of planning work, they're assuming here is the goal that you're given. Whereas we're starting to think about where do these goals come from, how do we specify their reoccurrence over days and weeks and months, and then how do we start to merge those goals with the goals that maybe are given dynamically by a user. Okay, so this long-term specification of goals is fed with the task executor. This is kind of the center part of our system. So this kind of mediates between different parts, so it will talk to the scheduler, it will talk to navigation, to actually get a task executed. So given we've got a goal, given we can come up with a plan for the goal, we then do everything within this box to step the robot through the necessary behaviors to generate those goals, to generate that behavior. So the task executor is somehow the kind of interface to most of the other bits of the system, the one that actually triggers the robot to start moving, to point its cameras at something, to generate something on the screen. Then what we look at, or what we looked at in the first version of the system, is scheduling. And I'll say a little bit more about what scheduling is, but given we've got a whole bunch of things we want to do during the day, given we know how to do them, we then need to work out which bit of those tasks do we do when, and perhaps where. And the when involves ordering, but also picking exact start times for those tasks. Because the robot is embedded in the real world, it's doing things in real time. And one of the interesting things is these routine tasks often have real times associated with them. So, go and check the mailbox at 3 p.m. So you have to actually be able to specify 3 p.m. Numerically here, and the scheduler has to be able to reason about the kind of temporal slack around putting a task at 3 p.m. So once you get into this kind of long-term planning and real-world service applications, time becomes a very natural part of your problem, as does resource, again, because we have battery to worry about. So scheduling requires a knowledge of, one of the interesting things about mobile robots is they drive around, they can't just instantly teleport, so we need to know how long it takes to get between particular locations. So that's actually one of the most one of the factors that dominates everything on a mobile robot is navigation. How long does it take to move? Whether it can actually reach something? What's the likelihood of being able to pass through a set of doors, for example, at a particular time of day? And that's again something we're going to talk about today and how we encapsulate that. And then we have the navigation system which can provide these estimates, but also is in charge of driving things around. So this is kind of the sort of whole system, and we're going to talk about at least these two boxes today. So I'm going to talk about scheduling and sort of the navigation duration part of it, and Dave will talk about our optimal navigation framework, and also how we've been extending this to deal with a more broader set of planning tasks. Any questions so far? Yes?
I'm guessing it does work, but does it work if some bit of navigation does not take the estimated amount of time? It turns out, oh, there's a door in the way, or there was a person in the way.
Absolutely, so that's one of the critical things. I didn't know how much need to go on this, but one of the critical things you have to do here is monitoring everything else. So our tasks might be, okay, you're going to look for an object, and you've got to do that between 10 and 11, and it's 9:45 now, so my estimate tells me I can get there in 10 minutes. So I'll wait 5 minutes, then I'll set off, and then if I get stuck somewhere, then I have to be able to flag something up here to say, I'm not going to be there on time, is that all right? Or perhaps actually looking for the object takes 20 minutes when I thought it was going to take 5, and that means the next task has to get blocked. So a key part of this overall architecture is monitoring things like timeouts and delays. And ideally, which we'll talk about in a minute, reasoning in advance, can I predict actually the knowledge of how long it's going to take at a particular time? Any other questions? Okay. So, I actually did want to ask you other questions. So, we're thinking about long term. We're thinking about robots operating for months at a time. The robots that I showed you before, last year, the blue one, Bob, ran for, 27 days continuously without expert intervention. So that is the robot autonomously navigating, doing tasks without someone fiddling with the code inside unless the robot asks them to. And so really working with end users. So 27 days is our kind of record. We're aiming for 60 this year. I don't think we're going to get close, to be honest. Everything's failing, but that's fine. What I want you to think about, maybe talk to the person next to you for just like a minute or two. Given all this, what kind of things are interesting from a planning, from a task, from an execution perspective for long-term performance? What kind of things should you care about? Think in very general terms, and we'll take a few answers. So please talk to the person next to you for like a minute or two with some ideas. What should we care about? What should we worry about if we want our system to perform for a long time? To perform well? What are the issues at a planning level, at a task level, at a general kind of even software level? Just to get you thinking. Talk to each other! Come There we go, it was muted. Sorry. Okay, it seems better. You don't really need this, but it's good for the recording. I'm going to move it out of the way. Okay, stick your hands up then, in your groups. Tell me some things that are important for long-term autonomy, long-term performance in a robot. Yes?
I think that one of the important things could be...
Can you talk louder, please?
Yes. How to collect experiences.
How to collect experiences.
And then how to conceptualize these experiences for long-term.
Excellent. Why are the experiences important? It's a great answer.
Because we are thinking about long-term performance. to be deal with unforeseen situations.
Yes.
So,
and that is how humans actually deal with that so and we want the similar capabilities for the robots. That is.
Okay, that's a great answer. That's one of the bullet points I'm going to show later. So, given that we have long-term performance, we've got an opportunity to gather lots of experience, or just data. Think of it as data. Okay? Lots of data about how long it takes for you to drive between one place and the other, how often you fail in particular bits of the environment. And then you can use that experience to improve your performance. Anything else? Someone I haven't heard from yet. Anyone else? Yeah.
Well, actually, this is perhaps following on from that point, but how can you take the understanding of one piece of knowledge and perhaps use it to understand something else you see? So perhaps two unrelated things, and then perhaps kind of find a relation between them.
Okay, so correlating experiences, transferring experiences. Yeah, that would be great. That's much harder than the previous thing, but that's also a good answer. Yes, excellent.
So maybe you have to perform some tasks that you didn't expect. So this changes your routine.
Yeah, absolutely. So coping with unexpected. Coping with unexpected input or maybe unplanned input for sure. That's a big point. Anyone on this side of the room? Is this the sleepy side?
yes.
Yes. You all had a big lunch and this side just had a salad, so they're all lively.
I can move and put my hands on
I'm not going to say no to you again. Give me a fierce look.
What if there is a small error on one of our measurements, but if we keep measuring like for 30 days, that's going to accumulate a lot, and then we're planning on the basis of something that's quite far away from the real measurement. So.
Yeah, so state estimation over long periods and general, so yeah, I think that and some of the previous answers sort of talk to one thing that's kind of key and think about how that is robustness. So errors that you may ignore on one day accumulate over long periods of time. The other thing in long run times is whatever can go wrong will go wrong. So if you've actually coded an execution framework and you've got some if statements to handle the return values of your execution system, there might be bits where you go, I'll just quickly put return false in here and I won't really think about the consequences. Then ultimately what happens is, maybe the first 10 days that branch isn't reached, but at some point it will be, something will happen, particularly in large complex robot systems. So robustness in terms of managing the execution of tasks and goals in your environment, but also in terms of input. So yes, being robust to the fact that a user could give you a new task at some point is actually quite a tricky thing. How can you choose whether to spend resource now or save it on the off chance that someone will give you a goal later on? It's an interesting big problem. I'd love to work on it. What we're not doing, but I'd like to do, is we'd like to learn predictive models of tasks to be given to the robot. So for example, if every day at 3 you're asked to come to someone's office to pick up some mail, it would be great to actually predictively include that kind of hypothetical goal into your framework, into your task. How am I doing this time? Okay, so robustness in all sorts of times is important. Timings in general, so a lot of this stuff is time-based. We really care about how long it takes the robot to move between two locations. A lot of tasks will be specified in time. Either a start time or a deadline. If you have to pick someone up to guide them to a meeting in a building, you really have to get there and get them to the meeting before the meeting starts. And you might want to be able to tell in advance whether you can do that or not. And finally, experience, which was the first answer we had. Given you're doing this every day, the first two things, robustness and timings, kind of allow you to survive. They allow your robot to run for a long time. Once you can run for a long time, you want to gather that experience and try and make your performance better. So that's a key part. And so, yeah, what we're going to talk about, one last thing, is what would be great is if we could have guarantees. So one of the things we're pushing towards in our research at Birmingham is not only doing these three things in this kind of architecture, but ultimately thinking about how can we provide guarantees on the robot performance. How can I tell you, I will get you there in 10 minutes with a probability of 0.98. So I'm going to be pretty likely to get you there on time. Or maybe I can get you there quicker, but I only have a probability of success of 0.6. And how can I start to make informed judgments about these kind of tasks along with verified guarantees on those systems? So that's something we're interested in. Okay, so we're going to start. Any questions before we move on? Okay. You don't need to be scared. Okay, guys, when I look up now, people are starting to look away from me going, oh my god, he's going to look at me. Okay, so we're going to talk a little bit about scheduling to start with, because that's one part of the system which is quite important. About kind of the long-term, at least sort of the day-level autonomy. So, I assume by now you've heard a lot about planning, you know a lot about planning. Planning is giving you an ordering of tasks to achieve some kind of goal. As I've said with the robot work we're doing, we also have time and resources, and there are planning techniques that can cope with times and resources, but we're thinking rather than a short time horizon of the next goal, we're thinking about how can we manage a large sequence of things the robot has to do over a whole day, for example. So here we'd like to move away from planning because it doesn't scale so nicely in these kind of conditions. And what we're going to do is we're going to think about individual tasks that the robot has to do, which is we're often in the scheduling world are called jobs. You might have heard of job shop scheduling. It's kind of one of these kind of scheduling problems. And scheduling, the role of scheduling is to assign a start time and potentially resources to the tasks that the robot has to do. So I'm going to say a little bit more about what tasks are in a minute. But one of the interesting things when doing this on a robot, they're kind of some things are harder and some things are easier. So in terms of a lot of scheduling problems, we actually simplify it massively in our work because we only have a single resource. What's our single resource? Someone tell me? in the overall? Yeah.
The robot.
The robots, absolutely, gold star. We only have to work out what the robot's doing. Of course we have to worry about the robot's battery, but really when we're scheduling, we're assigning resources to tasks, what we're thinking about is what is the robot going to do next? And as we only have a single robot, we've got a much easier scheduling problem, which is really coming up with a single, complete ordering for the task with time associated with the robot. There's more of a challenge, and that challenge comes, can someone tell me what they think the challenge is for scheduling on a mobile robot? Why is it potentially harder than, say, scheduling jobs in a factory?
There's nothing so parallel.
Trying to get other people to talk. Yes, thank you.
Well, I guess since the goal can change anytime, you need to reschedule all the time.
Yeah, you might have to reschedule. There's something else. So even if we assume a fixed set of tasks, there's still a challenge about being a mobile robot executing tasks. Yeah.
Well, if you have a given amount of tasks at different locations, it's a little bit like solving the traveler salesman problem, no?
Yeah, but there's a key difference on a mobile robot. Yeah.
The power supply.
The
battery.
The battery's a problem. Let's even assume we've got infinite battery. Yeah.
But the execution might fail, maybe, so you're not sure what happens.
Absolutely. So execution time issues. Failures, also duration. So if I'm driving, when I'm scheduling, typically what you do when you're scheduling is you assume how long it takes for you to get from A to B. So the robot has to move between tasks. And that movement is uncertain and variable. So you might say, I'm going to come up with this really good ordering that assumes, I take 10 minutes to travel between different tasks. And in reality, what happens is when I move, someone comes to take a photo because, look, there's a really cool robot in the office. And they all stand around it and take photos. And that means the robot can't move for 10 minutes because people are having selfies with it. And this happens all the time. It's something no one tells you in robot school. You really have to worry about. So it can really interfere with your travel durations and things like that. So you have to ideally have an approach that allows you to take into account the durations of travel. Not something we necessarily do here, but it's an interesting problem. So for us, when we say a task, we're going to mean a kind of bundled up system where we have a goal and a series of actions that achieve that goal. This task may come from planning. That's something we're looking at right now, but we won't cover in this talk, where you already planned for something and you have your goal and that's bundled up together. We're going to assume this task is a kind of black box that we're not going to reason about during scheduling, and instead at execution time we're just going to press a button and the robot's going to go and do those tasks. Okay, so what we want to do, so I'm going to talk a bit about one of our papers done by a PhD student, Michael Pelenka-Pedrova. This was in ICRA last year. So we want to know about scheduling, so we're looking at these timings. We want to worry about precise orderings, and we want to look at, say, 100 tasks at a time. So, it's equivalent of having 100 goals for your planning problem, but here we're not thinking about goals, we're going to assume we've got the tasks we need. We've already got the actions we need to achieve the tasks, we're just bunching them up into a block. And this is the thing that turns out to be more difficult. Can we do it for a whole day's worth of robot behavior? So, I've waffled on for way too long, so I'm going to speed through some of these bits. We've got our task, which we've already talked about, and we're going to define it with some variables. So we have our action, which is what we actually have to perform, and we're going to assume there is a duration of that action. D for duration, that's how long it takes us to do this. There are quite large issues again. It's a robot, it's operating in the real world. Typically we think about this as the maximum possible duration. That means that we're quite conservative when scheduling, because we always overestimate how long it takes us to perform any action, but it's a reasonable assumption. And we have a place where the robot starts executing and a place where the robot ends executing. They may be the same place, but they may be different places. And then each task will have a time window, a start time and an end time. This is the time when you're allowed to start executing and you have to be complete by it. So again, imagine, I want the robot to go and collect mail. Collecting mail takes 10 minutes, and you have to collect mail between 1 and 2 o'clock. Okay? Any questions about that? Yes?
Are durations flexible, or are they fixed?
Durations are fixed. So this is, we're going to assume this is the maximum possible duration. And in fact, going back to the kind of monitoring, if in our system, if we exceed this, there's an interrupt generated. So this is worst case time. Yeah. So And what we want to do is we want to come up with an approach where we take two tasks and we find some ordering, okay? The robot can only do one task at a time, so we have to take our tasks, say task I and task J, and come up with an ordering where we assign the correct start times such that they do not overlap. But we have this issue that we talked about before, where we have some navigation time that exists between the end place of the first task and the start place of the next task. Okay? And given these two time windows that are very broad and forgiving, in this case we can come up with two possible orderings. We have two tasks, we can do I then J, or J then I, and notice here that we don't have symmetric travel times. Okay? Going between two places may take a different amount of time depending on which way you go, due to various reasons. And as I said, this may not even be consistent every time we do it. And when we do this planning, this scheduling, what we're going to try and do is we're going to minimize some objective function. In this case, we're going to minimize user waiting time, which is the difference between the start of the window and the start of the task. So you're assuming that your user is grumpy, it's asked the robot to do something, and you want the robot to do the thing they've asked to do as soon as possible within that time window. Okay. Okay, so there's a fairly standard way of doing it, which uses something called mixed integer programming. We're solving this problem called mixed integer programming, which you're going to hear about more from Chris at the back. It was Chris, wasn't it? Yes. Back over this way. He's going to do a whole session on using these kinds of approaches. So I'm just going to fly through it. And what you'll find is a lot of what we're doing today is kind of just scratching the surface of other very, very interesting techniques. So you use mixed integer programming. For mixed integer programming, you set up a whole bunch of equations to describe your problem, and what you're trying to do is find assignments of numbers to those variables that solve your problem. In this case, our constraints are based on the things we already said. So what we have is we know that the start time of the task, t, and the time plus the duration must fall within the time window, okay? So that tells you, that constraint says that our action has to fall within the time window that it's been given. And then we have two constraints that say the tasks cannot overlap. So the start time of 1 plus the duration plus the time it takes to travel between the end place of I and the start place of J must be less than the start time of J. So that's just really putting this into a picture. Or we can do it the other way around. So here we have a disjunction. One of these constraints must be satisfied to ensure that our tasks do not overlap. Okay? So we set up these statements, and then we run a mixed integer programming approach which finds values for t, I, and tj. So those are the start times of the actions. Everything else is fixed. We assume we know this time in advance. So mixed integer programming is one approach for solving this kind of constraint system. Any questions? You're still with me? All making sense? You're allowed to say no. No? Okay. So, and then again, we're going to minimize, as I said, we're going to come up with assignments to all the different T's that minimize these possible things. So there might be multiple possible assignments of start times, and we kind of want to come up with assignment, the optimal assignment ideally that minimizes that value. Okay, so you do this, and this is work done by Colton et al. At CMU, did a PhD on using mixed integer approaches to solve scheduling tasks for mobile robots. And you get it, you implement the work from the paper, and you get something that looks like this. So as you add tasks, overall, this optimal mixed integer approach scales really, really badly. So what you see here is a 3-minute cutoff. That's maybe a bit tough as a cutoff, but what you want to do is really be able to be responsive to the user. So if I've got a set of tasks, and the user says, okay, I want you to pick up my washing from the laundry at 3 o'clock, you need to reschedule and tell the user, yes, I can do that. So if you think about this cutoff, you want to think about what's the longest amount of time I want the user to wait before I can tell them how long, whether or not I can achieve their task given the other tasks I have. So 3 minutes is actually a really long time for that. But that's one reason you might want to think about performance, speed in these kind of systems. So here, as we add tasks, the kind of the performance of this system scales very badly. But it's optimal. So up until we hit this red line, we get the optimal assignment of times. Here, because the mixed integer programming can be halted at 3 minutes, you get a valid assignment, but it's no longer optimal. So actually, we can always get an answer out of this system at 3 minutes, but we just don't know how good it is. Okay, so where does this complexity come from? Well, it comes from this choice. So it's the OR, it's the disjunction in the constraints that turns this from kind of a very simple assignment problem into a search problem. So, as you're at planning some school, I'm sure you all know by now that when you've got multiple actions and multiple choices, you end up with an exponential search space, and that's bad. And that's what's happening here. When you put 100 tasks in, and if you've got 100 tasks that all have the same start and end time, so they've got these really big windows, you're effectively searching over all possible orderings of all tasks in this space, which is why it, of course, scales badly. So, what's the solution here? So what we try to do in our extension to the content analysis system is we try to get rid of the OR. Okay, we decided this is a bad thing, we don't want that much freedom, so let's get rid of it. And what we did is we used something called Allen's interval algebra, or temporal algebra, which is a qualitative calculator for reasoning about the overlaps or lack of overlaps between two intervals, between two time windows. And it's a logic that gives you some kind of symbol, say j before I, if you get this kind of picture. So j before I says that j finishes before I start, which is why there's that gap there. So this is a very, very well-known algebra. It's used in a range of different planning and constraint reasoning tasks, and it's a great way of reasoning about time in a qualitative, non-metric fashion. So we can map these algebra symbols onto the use of that disjunctive constraint in our constraint formulation. So if we end up in any of these states where the tasks are already ordered for us, we don't need to put in either of the constraints in the disjunction. If we end up with one of these where there's some overlap, where the overlap has a kind of natural ordering, we can just decide to pick one of them. Okay, we can prune out the other option, and only in certain conditions do we actually keep both of the disjunctions. So what we're doing here is we're simplifying the set of constraints that we use massively at the expense of optimality, and perhaps even at the expense of finding legal solutions. Because we're limiting now by making some decisions, so by ruling out some constraints. So in this case we're not ruling out any, in this case we're not ruling out any, so here they don't overlap. Here there's only one possible legal ordering between those tasks. In these cases, what we might do, something else we tried, is just picking one that locally satisfies the objective function. So rather than allowing the mixed integer programming the opportunity to search over different solutions, we pick one that locally minimizes this constraint. The problem with that is it can no longer be optimal, and we may actually be ruling out legal solutions to our problems. So this is, you could call it a hack, right? It's very much a kind of greedy solution that we're taking to try and enable scaling. Okay, so we tested this on a test set of tasks from our real robot, because we care about real robot performance. We don't care about we do care about the computational and performance properties of this in the abstract, but what we wanted to do is see how it scaled on our own task sets. So this is from tasks from year 1 of the Strange project, where we had almost 1,000 individual scheduling problems that the robot encountered online during its operation. The smallest problem had 1 task in it. For these 2 different domains, the largest problem, this one had 135 tasks in the single scheduling task problem. This one had 71, and you can see the mean size, and the number of tasks was greater than 50. So 15 was important because that was the limit that Colton in his original work said, we're not going to deal with greater than 15. 15 was their kind of cut-off, but we found that a lot of the tasks when our robot was actually running had more tasks than 15, so that's kind of the number, I suppose. So this is a real-world scheduling set if you're interested. All of this is open source, and we can send you our task set if you want to play with it. And the approach we took goes from this kind of performance profile on the tasks to this. So we improve the performance greatly. Now we're only taking a tenth of a second to solve the biggest problems in our task set. The question then is, what is the actual quality of the schedule like? Well, we can look at this as a ratio between the optimal and the non-optimal, the Colton and ours. If we're above the line, it means Colton is better, the original work is better. If we're below the line, it means we're better. What you see with the dotted line is where the Colton work hits that 3-minute cutoff. So that's where the exponential gets cut off. And what you can see is when the optimal solution is allowed to run to completion, of course it often outperforms our greedy solution. Once you get past this kind of cutoff point and you stop the optimal solution early, we start to outperform, on average, the optimal solution, even though when it's been terminated. So that's kind of the overall take home from that. I'm going to skip the other results from the other domain, which are very similar. And I want to move on very quickly to start setting up what Dave's going to talk about in the next half. Sorry, no, I'm not. I'm going to ask Dennis a bit of questions before I rush on. So I know I did that bit really fast compared to the stuff that I
have you tried, because you know in advance the number of tasks, have you tried using a hybrid approach? So you use the other method when you have little tasks and your method when you have more tasks?
No, but we could very easily do that, yes. So that would guarantee us, and that's a nice hybrid approach to these kind of things. If you know the performance of your system, yeah, then for below 15 or below whatever, you go optimal and above you don't. So yeah, that would be a great extension. It's 2 lines of code, so we should probably do that. There was a question over there, yeah?
Just wondering how good LTL logic would be in this scenario.
LTL logic?
Yeah.
For this kind of problem, I'm not sure, but you'll hear a lot more about LTL in a minute, so I can hand that over today. I don't know. So you could create a big kind of temporal network over things this big. I don't know how it performs. Federico, you know about this stuff?
We're doing similar stuff with quantitative temporal reasoning.
Yeah.
And we scale up to what recently 500 to 1,000.
Cool.
But it's certainly not as fast as this.
Okay. So you can solve the problems but not as quickly.
Yeah.
But are you optimal?
No.
No. Okay. So there are interesting trade-offs. I think this is a big, reasonably unexplored. I mean, there are lots and lots of solutions to problems like this, but yeah, the scaling is another question. So it's something definitely worth exploring. Cool. I'm asking, I've got a question for you, but I'll ask that later when I'm running out of time. Okay, so the question we have next, so that was the timings. That's one way of getting timings for tasks in the real world. One of the questions is, where does this duration come from? In the scheduling problems, you always assume it's given to you. Sorry, the travel duration. Where does this come from? But this is the thing that we'd like to get through experience. And with navigation is a problem. This is Linda, the robot from Lincoln. This is at the Science Museum in London, somewhere down the road. Just to give you an example of why navigation is hard, why timings are difficult to estimate in advance, because you're going through these challenging crowds. Even in an office, again, there's people everywhere. So in our system, we have this layer here, which is our kind of experience gathering navigation layer. Very quickly, we have continuous navigation, so we're doing localization in a 2D map using adaptive Monte Carlo localization. On top of that, we've got a topological map. So everything we're going to talk about from here on out is going to be based on moving across topological edges. So these edges just tell you the connectivity. You're going to come up with a plan using Ross navigation stack between these locations. Okay, so the question is, given this and the timings, isn't it enough just to say, well, I know roughly the distance, I know how fast my robot moves, maybe I can estimate basically using kind of an assumption about a straight line. And with our first data set from the security applications that we did, we could look at our data and say, well, if I look at the mean time over all executions of a particular edge in the map, and I show you the 8 best matches between the mean time and that straight line heuristic you'd use, in some cases they're brilliant. So in some cases you get a near perfect estimate. Often this is because you're going down a straight line down the middle of the corridor. If you look at the 8 worst, then you're way off. Okay, so in these cases, what you've got, this is the mean time it took the robot to do this, and this is what your estimate would tell you. So here, that's for a single edge. When your edge is maybe your path is 40 edges long, by the end of that path, you're in a real mess with regards to time. So on top of our navigation, we have a monitored layer, which actually records things like failures and durations. So it's interesting because it also allows the robot to recover, but I'm not really going to talk about that quite so much. But this is just a quick plot. This is a topological map. The dots are places where navigation has failed during deployment. And the robot has deployed things like asking for help, which are green and red, backtracking to get out of the corner, which is yellow, and just sort of sleeping and retrying, which is blue. So these are all examples of places where the robot failed when trying to cross an edge in the topological map. And And this is actually a really essential part of robustness. So there are lots and lots of times, again, I'm just going to kind of fly through it, where over a kind of a 4-week deployment, we've got lots and lots of failures and lots of successful recoveries using these different approaches. So there's roughly that many per 17 kilometers traveled. That's a really weird statistic to present. I had a better version of that, but alright. Anyway, the important thing to say is what we're doing is on each edge, we're going to start gathering statistics. So I can record, when I start moving between one point and the next in my topological map, I can start a stopwatch. And when I fail to reach that point, or when I reach that point, or when I reach some other point that I wasn't expecting to reach, I can stop that stopwatch. And I can also record just the success or failure, binary value. Did I reach my target or did I not? And then by doing that, you've got a huge database of experience. It goes back to the answer earlier, the experience we get through navigating. And we can encode that into various forms of models. So one of the things we're doing in the Strands project is looking at different forms of predictive temporal models that will tell us in advance how long we expect a single edge in our map to take and whether we think that edge will actually be traversable. And all of these things will be parameterized by time of day. So you're asking, can I go through the edge in the cafeteria at 12 o'clock at lunchtime or 9 o'clock at night? And what we want to do is get different values out from those different questions. So at 9 o'clock at night, the answer should be, yes, it's empty and you'll be quick. And at 12 or 1 o'clock in the daytime, it'll be, well, you can go through it, but the probability of failure is a lot higher, and the duration will also be a lot higher. So you want a model that can capture your experience and allow you to access your experience in a way that is based on when you're going to execute the task in practice. So this is stuff that we've done some papers on it, look at, for example, fitting Fourier-based models, so periodic models to data. So this is the raw data of a traversability of a particular edge in your map. Then what you can see is when you fit some of these frequencies to it, you get a nice model that says this door, in fact the door was open in the afternoon and not in the morning. As a kind of very general conception about how we're doing that. So you learn through experience that this door is open in the afternoon, not in the morning, and you can use that in your planning. And this is, I think, quite exciting problem to be looking at, given our long-term experience. What can we capture, how can we capture, and ultimately how can we model it under the hood with machine learning approaches that allow you to kind of really access what is the kind of constant underlying properties of your domain, and what is noise, can you extract out the noise? And it's not something we're very good at yet, I don't think. Okay. So this is just a quick video showing you some edges. The predicted speeds are in colours. The width is the probability of success. And what you can see actually in one of our domains is just the doors. Around the doors you really start to suffer. So a lot of the stuff in the general open space is quite constant in terms of probability. The speed in general is always constant actually, once you've learned it. But it's the probability of success around doors and some tricky navigation areas that challenge it. Okay. So how do we use this? Well, we get these probabilistic models, we take our topological map, and we turn it into a Markov decision process, where the action in the Markov decision process is moving from one node to another. The cost of that action will be based on the time, and the probability of success of that action will be based on the experience probability of success. So that's how we capture the experience. And that's something that Dave's going to talk about in the next part. So hopefully I've motivated the need for scheduling and the need for robust execution and gathering experience at the same time. And that is more or less where I am going to stop. I've maybe got time for one or two quick questions while Dave sets up. So I really rushed to the end, but the general idea is scheduling gives you times. You start running with that, you gather experience, you can feed that experience back in using predictive models and then capturing the statistics from those models into MVPs and LTL, which Dave is going to talk about. Yes?
You showed there that you have, like, if you move from W1 to W2 with 0.1, you get to W3.
Yeah.
Does the robot know what that is, or is that just something unexpected? Like if you fail going.
When you say that is, what is what bit are you talking about?
Yeah, like I understood that it's like move from one place to the other place, and you have a 10% chance of failing.
Yeah.
Does the robot then know where he is? Like, can he predict that? Or
yes. So we're always localized, and we know where we are. We know we're in a particular node. And so the robot, what will typically happen is a failure will either be you end up in a node you weren't expecting to be, that's typically quite rare, our robots are very well localized, or you eventually give up, so you just time out or something cancels you and you didn't reach your target. So what might happen is you're trying to get somewhere and there's an obstacle in the way or there's a person in the way and you end up getting too close to a wall and you can't get away from the wall, and then ultimately something says, look, you've taken too long, I'm going to cancel you. So you know you failed, you know where you are, but you're not where you wanted to be in that action.
Yeah, well, I can understand. How you recover when the duration of an action expires?
Okay. So we don't really recover that. Well, okay, there's two answers. In the general sense, we've kind of screwed up a little bit, and we could go and replan with the new durations. The other answer is you can build a policy over both location and duration. And what we're doing at the moment, and what you will see in the system that we use in the practical bit later on, is you can have different durations for different outcomes. So you know how long it takes you to succeed, but you might also have multiple failure models that you've learned. And then in your policy, you can say, well, if I fail in this way, typically it takes me this long, and then I might already have an action built into my policy for dealing with that kind of failure. So if you know how long it takes you to fail in different ways, you can already use that in your policy at planning time. Okay, I'm going to hand over to you, okay? Thank you very much.
Okay, thanks Nick. So Nick's given you an overview of this whole system. We talked about some of the key aspects, and then he's dived down into bits of it, in particular this scheduling, and shown you how some of the messy details on what it looks like. Okay, so I'm going to now dive down into a different aspect of the system, which Nick has just motivated towards the end there. And that's mainly this idea about guarantees. So you've got these long-running systems, you want them to be reliable, robust, and you really want some kind of guarantee these things are going to work. Okay? And at a high level, but also at a low level. So if you've got these scheduling algorithms that rely on reliable estimates at the time for a particular task, we want to know how for particular navigation tasks, how we can get strong, reliable guarantees on how long these things are going to take, how well they're going to work. Okay? So that's what we're going to talk about in this part. The other key word here is formal. Okay? So this part of the system, we bring in methods from formal methods, formal verification, and we use these to come up with these guarantees. Okay? And I'm going to try and show you how what the bridge is between these two worlds. And as also mentioned, so this is going to come across in what you'll see in the practical sessions later. Okay? So I'll try and focus on the bits that you will find helpful for that. Here's the plan, or more than the plan. So I'm going to start with a quick diversion and just tell you what what formal verification means in a general sense, and in particular the variant we use here. So I want to just kind of explain what you can do with it in general, and then in the rest of the talk focus on what we do with it in the context of robot navigation. For the latter, I'm going to talk a bit about MGPs and how we use them in this context, and then explain what we can do with linear temporal logic. Okay, so that was asked before. This is going to be a way that we specify tasks, and because it's all done formally, this is the key kind of glue that gives us a way of automatically coming up with good policies for our robots, but in such a way that we can get formal guarantees about how reliable they are, how long they take. This kind of thing. So this is kind of the glue between those two parts. There's more stuff in these slides on extensions towards multi-objective. I don't think I'll go into that today. Okay, good. So, as I said, I'll start with a quick diversion. So formal verification, if you haven't seen this stuff before, is basically applying rigorous mathematical techniques to prove the correctness of your system. It could be software, hardware, it could be a protocol, it doesn't matter. Roughly speaking, you're coming up with a mathematical proof that your system is correct in some sense, but you're not doing that in pen and paper, you're doing that with clever tools and techniques and algorithms. Okay? So this all comes from that world. In particular, we're looking at systems with some kind of probabilistic behaviour, because as you've seen, you are trying to verify things in a noisy environment. In fact, I mean, that's what we'll see today. In general, and then this part of the talk is just very generally about verification of systems. There's many situations where you want formal guarantees on correctness or reliability, and there is some kind of stochastic or some kind of uncertain behaviour. Okay? So that might be because of hardware failures, it might be because of sending messages in a protocol across some wireless network, for example, or in the context of robotics, it might be because your environment is noisy in some sense. Okay? Also, randomization is very common. Verification is used for protocols, they often have randomization. Okay? So in a general sense, there's many places where we get kind of stochastic environments. And the corollary of that is that what we want to verify is usually quantitative in some sense. Okay, so these are techniques coming from formal verification, which is about correctness. So it's checking, classically you take a device driver for your some piece of hardware, you verify that it never hangs or it never gets into this particular part of the code. So kind of very qualitative stuff. Once you move into this world, the properties you're going to verify, these guarantees you're going to come up with are very quantitative. Okay? So a nice example would be a controller for an airbag, and here you've got a controller interacting with some physical components that fail, so it's probabilistic in some sense. And you might want to check, for example, the probability of the airbag failing to deploy within 0.82 seconds of being triggered is at most 0.01. Okay, so you've got some notions of time, you've got notions of probability, but you've got what should be a precise, formal, quantitative guarantee on latent behaviour, in this case reliability. Okay, so in general, this mix of formal verification with probabilistic systems, it kind of goes beyond correctness, really it's moving towards reliability, timeliness, performance. So anything that has this kind of probabilistic aspect to it. Okay? There's different ways you can do verification. The most common is to use model checking. And in particular here, because we're looking at stochastic systems, we're going to use probabilistic model checking. Okay? Very roughly speaking, that means you are building some kind of model of what your system does. So you've got some notion of what the states, configurations of your system are going to be, the different places you can be, what the transitions between those states are, and some information about the likelihood of making those transitions. Yeah, question? No? Okay. So this is going to capture your system somehow, what it does. Because you've got this probabilistic information, it's probably going to be a Markov chain, or here it's going to be a Markov decision process. Okay, and that's details of that we're going to come on to in a bit. But you've got some precise full model of what the system does, and that's the level at which you're reasoning. Okay, so later in what we're doing here, this is going to be the kind of picture you saw in the next talk. Okay, so these are going to be locations of a robot. This is going to be information about how it moves around and what level of uncertainty, and then we're going to make guarantees upon that. Okay, more generally, this could be almost anything. It could be a protocol, it could be a bit of hardware, it could be many things. Okay, but we have some formal model, and then we want to verify that. And as I said, what we need to have is also a formal way of writing down what the properties we want to be true of. Okay? And we're doing that with temporal logic. I'm going to talk a bit about LTL, linear temporal logic, in a bit. This is not LTL, but it is a formal logical description, in fact, of the property I just showed you on the previous slide. Okay, so this property here, don't worry too much about the syntax, but it's a piece of, it's a formula, a temporal logic called PCTL. And it basically means exactly what I said on the previous slides. The probability of this event happening within some time frame is above some threshold. Okay? And this, I'm trying to give you just a high-level picture, but this has a very precise syntax and semantics. And once you have tools that can take these models, take these properties, and go away and check that the model satisfies the property, then you've got a very strong guarantee that your system is correct in the sense that you specify. Okay? And that's the kind of level of formality we're looking at. And the idea of model checking is that this stuff is all fully automated. Okay? So you have to come up with your model somehow, you have to write down your property, but once you've done that, you've got efficient tools that can go away and do all the computations that are required and tell you if this thing is true on this model. That's the essence of why model checking works. In this case, probabilistic model checking. So then the last part of this, just quickly try and give you an idea in general why this works well. I mean, the key point here is we're getting exact results, we're getting guaranteed, we're getting optimal results. Okay, so once we've built this model, we're really exhaustively exploring it to check whether this property is true. Okay, so we're working out all the possible states, and we're working out really what is the exact probability of this event, and we're checking that it's suitably high. Okay? As I mentioned already, it's fully automated, so we use a tool called Prism. That's underneath all the stuff that you'll see later on today. And we're going to focus on MVP, which is generally quite widely applicable. So I should also mention the downsides. The fact that you do build this exhaustive model with this MVP or whatever it is, and explore it and solve it, means there's obviously going to be some kind of trade-off in terms of scalability. Okay, so if we want to have guarantees, we want to have formal notions of reliability, that's great, but we have to do things at a certain level of abstraction. Okay, so we have to have some model that we can exhaustively build and analyze. And what you see here is a nice level of, because we work at this kind of navigation level map, we've got these locations, we've got movements between them. This is an abstraction to some extent, but once we trust that abstraction, we think this is a good representation of our system, that's a level that we can work at effectively and get some results that we believe in. Okay, and that's the level at which we come up with guarantees. So I keep hinting at the robot case, but in general, this works in many different domains. This idea about building a formal property model, coming out with a formal property you care about and checking it, this has been used in communication protocols, computer security, systems biology, many things. Okay? So this is kind of a general picture. The rest of this talk now, I'm going to dive in and say what this means or how it's used in the context of robotics, in particular navigational planning. Okay? So that's a general picture of that. Any questions about that before I dive in? Yeah.
I'm so curious about how that threshold. So once you do exhaustive search, you're basing that on your MVP model of the world.
Yeah.
And if you have a very, very tiny probability of failure on somewhere, you're going to reach that state a very small number of times.
Yeah.
Is that enough? Have you got some sort of a measure of how, if I saw this state just 1 or 2 times?
So generally speaking, there's 2 ways in which this is exact. One, you're exhaustively storing the state space, and 2, you're relying on solution methods for these models that can give you arbitrarily precise results or exact results. So I mean, this is again where the trade-off between scalability and accuracy comes in. But we're always going to be looking for methods that compute definitely the optimal probability, for example, or the precise optimal probability. And so if it turns out to be very, very, very small, which is the kind of thing you would expect to see in these kind of domains, then you've got techniques that can zoom in, find the relevant part of the model, and then solve those values precisely. And it's a trade-off. It's the trade-off between exactness and scalability. Okay. Any other questions? Okay, good. So that was the more general part. I'm going to dive in and show you how this works, in particular when this thing is an MVP, representing a kind of robot navigation problem, and these kind of things are using a logical temporal, linear temporal logical or LTL. Okay? So how many people already know MDPs to some extent? Most of you. Okay, so I mean, we don't need too much detail there, but that's good. How many have seen things like temporal logic or LTL? A couple. Okay, good. So I'm going to cover this at a reasonably high level, but enough that you can see kind of what is going on underneath. Okay. So MDP, most of you know. So this is going to be the kind of level we're going to talk about things here. We've got some states. In this world, they're going to be the locations of our robot. Okay. We've got some actions. Here they're A and C, for example. And we take an action in some probabilistic outcome. Okay. This is the intersection of 2 different worlds. Okay? So in the verification world, this idea about non-determinism, the idea you've got different actions in each state, can be used for many, many different things. It could be for control, it could be for verifying the kind of worst case behavior of some system in an adversarial setting. For example, what's the worst case scheduling of different processes? Lots of different things. Here I'm mainly going to focus on what's relevant for this robotic situation, which is going to be in control. Okay? But in a general sense, you see a lot more of these different things. Also, the terminology is usually a bit different. So here, we're talking about strategies of MDP. But if you know MDPs in this setting, you almost certainly call them policy. Okay, so when I say strategy on this slide, this just means policy. I'm just using terminology that's taken from the world of verification. Okay? So we have MDPs, we have strategies or policies which basically just decide how these things are resolved. And then once you execute a policy on an NDP, you get some kind of probabilistic execution, and then you can start to measure things on this and talk about whether it's good or bad. Okay? So for a given policy on a particular NDP, I can start to answer these kind of questions here. So for a particular policy, is this thing true, for example? Okay, and that's how we're going to connect these things here. So there's a notion of, again, in this world, it's important what particular classes these strategies are. If we start with very simple properties, we only care about memoryless strategies, where we just pick the same decision in every state. Once we look at linear temporal logic, then we move towards more complex types of strategies. So they might need finite RAM, you might need to keep track of where you've been so far, and you might need randomization. Okay, so I'm going to skip over that stuff fairly quickly, but it's good to know how you understand what this strategy would map down to what will be the controller for your robot at the end of the day. Okay, so it's important, not just in a theoretical sense, but in a practical sense, how complex these strategies, these policies are. Okay? But we have NDPs, we have policies. I want to now try and connect that to the kind of properties we check in this formal verification sense, and in particular with RTL. Okay? So I'm going to skip over this slide. The key point here is basically looking at just computing optimal strategies. Okay, so let me just dive in with an example. So I'm going to use this as a running example. Okay, so this is an example of a little 6-state NDP representing some robot moving through a grid. Okay, so we've got 6 locations, and the idea is in a particular location you decide you want to go in some direction, but because it's a noisy environment, because you've measured that there's likely to be obstacles here, you know that if you do that, you only achieve it with a certain probability. Okay? On top of that, we've got some notion of likely durations for each transition. So you know that not only is there a chance that you might not be able to get there straight away if you try, you know something about the expected duration. Okay? So to introduce this idea of RTL, for now I'm just going to skip the idea of time and just talk about probabilities, because that's enough. Just think about this as always having some kind of information about time on the edges as well. And that's more or less what Nick left us at the end of the last talk. So you've got this idea about locations, you saw this topological map, and that's what meetings correspond to, and then you know something about the likelihood and the timing of moving between those locations. Okay? So that's the running example. In reality, they look more like this. So this is exactly one of the examples from the deployments that you saw earlier on, and this corresponds precisely to the kind of MVPs we're talking about. Okay, so this just gives you an indication of the, let's say, the level of abstraction we're talking about. So we're reasoning about planning and navigation at the level where the locations in this picture, so you've got a few spots in the room, you've got several spots in a large corridor, these correspond to the states in your NDP, and you've got some idea about how you move between them. Okay? So I'm going to drive back down to at this level, but just think about that as corresponding to these kind of maps. And again, when you see this in the afternoon, in the second practical session, you'll be looking at things at this kind of level. You've really got real data being used to generate what these MVPs look like underneath. Okay, good. So we've got this simple example. Let me first of all show a very simple example of an optimal policy, and then I'll extend that to talk about how we can use this linear temporal logic. Okay? So here's an MVP. Let's forget about kind of time, expected time, cost, and so on. Just think about the probability of some event, the probability of some task being achieved. Okay? So this thing here is a temporal logic expression saying what is the maximum probability of reaching some goal state. Okay? So the green bits here are just these labels on the MVP, and they're what connect the MVP with the temporal logic expressions that we're going to use. Okay? So it's the simplest class of property to think about. How do we, in this MVP, how do we maximize the probability of getting to this goal state? Okay? I'm not going to go into too much detail, because the idea is really to go on and show you what LTL brings to it, but we can do that quite easily. Okay? So we can use standard techniques, which essentially search over all memoryless deterministic strategies, and we use some kind of classic techniques like linear programming, policy iteration, and this kind of stuff, which, because we only care about the optimal policy. Okay? In this world, we're restricting our attention to NDPs that are small enough that they're interesting to model the real world, but we can always come up with the optimal, the worst of the best case policies that we care about. Okay? So that's why we're mentioning many other ways you can do it, but that's the kind of stuff that we're focusing on here. So in this case, you would say, for example, this thing marked in red is the optimal policy for maximising the chance of getting to some goal state. Okay? And here, this is a very simple temporal logic formula that's going to capture what that goal was. So to take that further, I'm basically going to expand this bit here. So this, you can think about actually this F goal 1 as being a very simple linear temporal logic formula that says what the task is for this robot navigation problem. Okay? So how do we specify more complex properties for this thing here? And that's what I'm going to tell you now. So how many people have, you've seen LTL, if you haven't seen LTL, how many of you have seen propositional logic reasonably recently? Hands up if you know propositional logic. Most people. Okay, good. So if you do, this should make sense. If you don't, just look at the examples. There's several kind of clear examples that should explain what kind of thing you can do this. Okay? So LTL is a logic for describing executions. Okay? In this case, desirable tasks that we want our robot to execute. So this is the syntax for LTL. Basically, if you look at the left part from here, this means we're just looking at propositional logic. Okay? So these A's, these propositions, are just going to be these labels on our MVP. And then you can combine these with conjunction negation. So straight away you can talk about, for example, I'm in a goal state but not in a hazard state. Okay? So you can talk logically about which bits of the world you're in or not in. The rest of the logic, these red operators here, X, U, F, G, and so on, you sometimes see these written as boxes and diamonds and such things, but here we're going to use the letters. And these let you talk about temporal order about events. Okay, and that's the key to LTL. So, for example, this X something says that something is true in the next state. F says that F psi multiplies eventually true, and that's exactly what we have here. Right? So in the previous slide, this says that eventually we get to this goal state. Okay? G means that something remains true forever, and U is a bit more general, this is until. So it says that the second part eventually becomes true, and the first part always remains true up until that. Okay? So they're the kind of key individual operators you've got to reason about time and the ordering of events. So it's a very simple example, you can plug it in. These are not kind of robotic style examples, these are the kind of classical things that you would use LTL for to specify properties of some system you want to verify. So you might say, it's globally, it's always true, you don't get to a point where two processes are both in their critical section. Okay, it's kind of classical computer science properties that you don't want two processes to interfere with each other. The key point is you can actually combine all these things. So here you've just got a single G. This stuff becomes more useful when you start to combine temporal operators. Okay, so let's look at these. So I've just repeated the syntax here. So here's some simple examples of common patterns that we use in LTL that say something about now slightly more complex behavior. Okay? So this G again means globally or always. So we're saying always this subformula is true. And this subformula says that if A is true, then eventually B must be true. Okay? So this is something that's true or not of some particular execution of our robot. And it's true if, along that whole execution, every time you see an A, so that might be some trigger event, then somewhere down the line, B is later triggered. Okay? So think about these as being something you can evaluate on a single possible execution of your robot. So similar style, we can say something about A immediately triggering B, always. GF, this says always eventually A, so that's basically saying that something happens infinitely often. Or flip it around, it says that something eventually becomes true and stays there forever. So eventually we reach some kind of good state and we never leave it. Okay? So these are kind of simple patterns, and then because you can just combine these things using this logic, you can come up with fairly complex specifications. Okay? So here's some slightly, still fairly simple, but more indicative examples of things in LTL. Okay? So these are robot task specifications written as LTL formulae. I'm using, well, the first one I'm using the same propositions from that simple MVP. Okay, so we've got a hazard proposition which is labeled as a state we want to avoid. I've got goal 1 proposition that labels some particular good state that we want to visit at some point. So this thing here says G, not hazard, so it's always true that we don't go in the hazard state. and we do reach this goal state infinitely often. Okay, so again, if we look at one particular execution of our robot, and we look at this particular property, we can say whether that is true or false. Okay, so we're writing down something, in this case, that we want the robot to do, and then if we look at what's happening, we can say, is this true or false? Okay? And again, this is going to now make things formal and precise, and we start to reason about guarantees and stuff. Another simple example, do we eventually get to zone 1, and then after that zone 4, whilst never passing through zone 3? Okay, so again, we're saying something precise about the ordering of different events, just using combining these simple couple operators. Okay? Does that make sense?
Just a question about A is true infinitely often. I read that as A will eventually be true in this system.
So just FA, right, so G there,
yeah.
That would say, along you think about single execution. Okay, so along the single execution, FA says eventually A is true. This is now saying that thing is true all the way along.
Yeah, so FA is true in every node or state or whatever.
FA says that A is true once in the future, and then G says that even once that's happened, and we carry on beyond that, then it's also true. So it will happen again and again and again. Cool. Okay, does that make sense? Any other questions? Yeah.
Something like a parser to turn English into Latin seems pretty straightforward.
People try and do that, it's not so straightforward. I mean, the better way to do it is that, well, like I've got here, is a reasonable set of patterns that you can kind of, especially for particular application domain, there's a set of patterns that you can use and you can combine. And so like here you've got two particular things you want to be true, both of which are in a simple kind of form, and you combine them together because you got this. So people do, I don't know that work very well, but there is people who kind of write down kind of goal, kind of task specification languages and map them to more form. So that's kind of moving in that direction. But I mean, maybe going all the way from, say, natural language to RTLs, but etc. Going the other way is doable. You can kind of unpack these and say what they mean and then you go those things. Any other questions? Okay, so this stuff, like I said, you're going to see in the practical session later on, I hope. But these are some simple examples that you can kind of fall back on and get a rough idea of what this stuff means. So the remaining thing here is to kind of glue this stuff to the MVP part you've seen already. Okay? So this is basically specifying a task, or in a kind of formal sense, it's saying if I've got some execution of my robot, I can tell you whether or not it satisfies this particular thing that I want to be true. Okay? So to connect that to the MVP, well, we can talk about the probability of these things being true. Okay? So going back to this idea of writing down probabilistic temporal logic formula, this thing here says with probability at least 0.7, this task that I just talked you through is satisfied. Okay? So that's something you might want to be true on a particular system. Or I've also shown you these ideas about just maximising the probability of some event. Okay? So I'll formalise now what my robot to do. In the MVP, how can I maximise the probability of that thing being true? Okay? So you've got the idea of a task specification, and then in this case, it's just something that we want to be as likely as possible. Okay? Now we can go a little bit further back to that. Yeah, the other thing we can do is we can talk about costs and times. Okay, so again, at the end, Nick was talking about you've got these MVPs, these kind of navigation graphs, and we know something about the expected time to move between each node. Okay, so I've got a formal model of my system with probability of the time. I've got a formal definition of my task. I haven't written the formula, but what I can say now is how do I maximise the probability of this task being true in terms of picking the best policy, or how do I minimise the expected time to satisfy it? So how do I pick the policy which achieves this task in the best possible expected time? Okay? And then you need to restrict yourself to some particular subclass of LTL, but that's a detail we're going to get. Okay? So why would we do this? Well, the key thing here is that we're using LTLs as a flexible, unambiguous definition of task. Okay? And the real reason for that is we're then using that to come up with some guarantee on performance. So if we write down our task in this form, or we generate it in this form, and then we solve our MVP somehow, we can say, well, I know what the task is formally, and I can guarantee you the policy I'm going to give you for all that is optimal, or it definitely satisfies this kind of property that you require and satisfy. And so that kind of connects the what you want to be true with the kind of formal guarantee that you're producing as a result. And the other aspect of that is that the guarantees you're getting are on meaningful properties somehow. Okay, so this means something. We're talking about the probability of something you understand being true, or the expected time of this thing being true, being minimised somehow. Okay? And that's in contrast to what you might do in a planning environment is just say, well, I'm going to come up with my own custom reward structure which encodes a particular problem, and maybe I don't care that it's optimal, but I can show that if I do that, I come up with a very good policy. Okay? You might come up with an optimal policy, but you've got an optimal policy for some kind of carefully crafted reward structure, maybe with some discounts you would apply to it, then it might work very well, but it's very hard to say what guarantees you can come up with and what that means. Okay? So the reason we look at these kind of ways of specifying what is the optimal policy is that once we get it, we've got a very clear formal definition and also a kind of a reasonably intuitive explanation in English of what that means and what we can say about how good it is and what how much we trust that result. Okay? The other aspect is that this idea of RTL, it does have very efficient, well, it has fully automated techniques which on a reasonable size MVP can be done quite efficiently. So I think I'll kind of touch on that now and show you very roughly speaking how this LTL and MVPs can be checked. I won't go into the detail, but the idea is that if you've written these down in this form, not only is it unambiguous what it means, but there's techniques which can map that into fully automated algorithm techniques that go and make sure these things are optimized. Okay. In fact, yeah, okay, so let me just spend just 2 minutes trying to give you a hint at, given one of these properties here in RTL, given an MVP, how we can go and check that these things are, how you define the optimal policy. Okay? And the way we do that is we have a connection between LTL and automata. Okay? This is kind of classic results from automata theory. But the idea is if you take a particular, this is the LTL form that we had before, so it says globally not hazard, I've abbreviated it, and infinitely often we get to goal 1. Okay? So that's simple logic. That's something a human can understand and can work with. What we can do is we can automatically map that to an automaton. Okay? So this is in fact a deterministic Buki automaton. If you don't know what that means, it doesn't matter. The idea is it's an automaton view of the same property. You can think about it as kind of a monitor. Okay? So this gives you an automaton where you start at the beginning, you plug into it at every time step the current state of your system, and by doing that you can tell whether or not this thing is true. Okay? So more precisely, you start here, you look at your current state and say, well, have I reached the goal, am I in a hazard state, and depending on what's true, you jump somewhere else. Okay? So you kind of feed in an execution of your robot into that automaton, and then in this case we want to visit this kind of accept state infinitely often. Okay, so the precise type of automaton is going to dictate what this means, but the idea is you're going from something that's purely textual to something that a computer can basically plug in and work out whether or not your property is true. Okay? And a bit more precisely, kind of flicking over this quickly, but if you take this MVP that we had before, you take the property that we cared about, we said that we always avoid this state, we'll get to this one infinitely often, you construct that kind of monitor property that I just told you about, you can compose those two things together, and you get a larger MVP that looks like this. Okay? So that's a product MVP, and the idea is it captures all the things that are going on in the original model, but also keeps track of what's happening in that model with respect to the property that you care about. Okay? And now if I want to say, well, for that MVP, what is the policy that maximises the chance of this task being satisfied, then what I actually do is I look for kind of cycles in this MVP which have one of these accept states, and then I go back and say, well, how do I maximise the chance of getting to here, and that gives me exactly the policy. Okay, so it's basically taking a more complex property on a normal size MVP and reduced it to a simpler property, just maximising the chance of getting to some part of the model in a larger MVP. Okay. Yeah?
How large are the entities you're typically dealing with?
So it varies. I mean, this is the product. So in the worst case, it's literally the number of states in this multiplied by the number of states in this. Depending on this could be anything to, let's say, 10,000 locations. This might have 10, 20 states if it's a reasonably complex property. It could vary in both directions. It could have a smaller navigation map, a simpler or larger property, but usually you end up with kind of a full product of those two things. So it is both have limitations. At the end result, we don't really want NDPs that are bigger than 1 million, 10 million states, let's say, and that complexity might come either from here or here. Probably this bit is larger than this bit, unless you have a really massive property. Okay. Any other questions?
What do you maximize or minimize over this?
So the product, what I'm doing is I'm finding cycles in my model that have the exact property that I got from here. So I maximize the probability of reaching one of these cycles. So that's kind of basically that reduces back to the property in the circle before. So if I can find the best deterministic memoryless policy which maximizes the chance of getting to here, that will correspond to the policy in the original MDP that maximizes the chance of this.
So is that maximizing the probability of reaching a particular state in this composed MDP?
So it's set of states, yeah. So I'm looking, what I do is I find kind of closed bits of the MDP that are cycles, and I say, right, I just want to get to that. I have a set of states, a set of target states now, and how do I maximize the probability of reaching that set of states?
But this is not a standard, so you cannot use any of the shelf MDP solver to do that. That's sort of a...
Well, I mean, that, once you've done this kind of graph analysis to work out what this bit of the model is, then that's just a problem you can plug into policy iteration or value iteration or any standard technique. So maximizing the probability of reaching a set of states is easy. I mean, given that we're restricting ourselves to, we've already made this kind of trade-off with ourselves that we're looking at NDPs in the end that are small enough to use these kind of examples of awesome techniques. And if you do that, and it's all kind of finite state, then that problem is not difficult. Any other questions on that? Okay, I think. Yeah, so I won't say much about here, but what you can do is you can take the same kind of formula, and rather than looking at the maximum probability of achieving that task, you can look at the minimum expected time of achieving that task. And that's really connecting this idea about LTL as a task classification language with the kind of the simple graph we saw at the end of the next talk, where we have both the probabilities and the time, and we want to basically just do something specifying LTL as quickly as possible. Okay, so I've kind of not included that here, it's basically the same idea. You get an autonomy to build a larger product like this, and then you do some computation behind it. Okay? So what you'll hopefully see in the practical session, all this stuff is going on underneath. Okay, so you will be basically writing down some formula like this in some form. And underneath that will be translated to one of these things. This map will be constructed from a navigation design, and then this thing will be constructed and solved, and that's all underneath. So all you think about is what is that formula? What is my map? And it should spit out some kind of policy that you can plug into your development. That's the level at which we want the users to understand. Okay. So basically, right, so what I'm trying to do really is show you how some of these ideas from formal verification, which builds in kind of classic stuff from logic, automata, and all sorts of different areas, how that combines with this world of probabilistic models and particular MDPs, and bringing all those things together, how we can come up with rigorous guarantees for the behaviour of these kind of, for example, robots operating in stochastic environments. Okay? So I've given you kind of a very brief overview. This bit was mostly based on these two papers from ICAPS and Chicago last year. For the probabilistic verification in general, there's loads more information on the PRISM website if you're interested. Okay? But for that part of the talk, that's been done. Thank you.
it's break time.
It's break time now, and yes.
Before you go on break, I just have a quick show of hands so we can plan what we're going to do afterwards. Please, can you put your hand up if you're able to successfully install all the things we asked for the next session?
It crashes.
Okay. Okay, cool. Put those hands up really high for me, please. Just so you can, well, even the people that had half hands up. Okay, now keep your hand up if you're comfortable with Python as well. You had to have your hand up to start with. You have to have a working system out of your Okay, alright, cool. So we can make stuff work, I think. Alright, thank you very much. Okay, great, we're good to break.